Let's draw some Lewis structures for covalent compounds. We'll do simple ones. What time is it? 8:03. We're going to do simple. So again, we already gone over dot diagrams. We're going to do simple Lewis structures for covalent or molecular compounds. Um, and uh, and then maybe we'll do like a double or triple bond. We'll talk about that, and then we'll call it a night. And we'll be able to end a little early tonight. So it's awesome. So let's go till 9:50 on these nights, which that's, my God, 9:50. Okay, here's how drawing Lewis structures for covalent molecules works. We try to draw our Lewis structures to satisfy the octet rule for everybody, except for hydrogen. If you look at a periodic table, hydrogen is not trying to get 8 valence electrons. The noble gas that hydrogen is trying to look like is helium, and helium only has 2 electrons. So hydrogen does not follow the octet rule. Hydrogen follows the duet rule. It only needs 2 electrons. Everybody else is pretty much trying to get to 8. We'll eventually look at some exceptions. Boron is happy with 6, blah, blah, blah. But for now, everybody trying to get to 8. Okay, everybody's trying to get to 8. So that's called the octet rule. So that's what this slide here is trying to say. Hydrogen forms stable bonds by sharing 2 electrons in covalent or molecular compounds, and everybody else is doing 8 to fill that octet. So how do we do this? Well, here's a set of rules, but we're going to do so many of these, you won't have to memorize these or really think about these rules. The first thing we do when we're trying to draw covalent or molecular Lewis structures is we add up the sum of the valence electrons. So we get the total number of electrons in the atoms, okay? Then we connect everything with a bond to the central atom. We'll talk about how we know what atom is the central atom. And then we try to satisfy the octet rule for everybody, except for hydrogen, using pairs of dots called lone pairs, okay, called lone pairs. So let me walk you through how to do this. Here we go, folks. Oh, my goodness. If you are going to go on to take organic chemistry, before you walk in for your first day of OChem, make sure you brush up on Lewis structures. Do not walk into that class unable to do Lewis structures. Don't do it. It is not going to go well. No, 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 no. All right. Here we go. F2. First of all, let's confirm this is covalent or molecular. If you find fluorine, fluorine is a non-metal, so 2 fluorines together, this is going to be a covalent or molecular compound. That's going to be a covalent bond between the 2 fluorines. When we are doing covalent Lewis structures, I do not do dot diagrams, okay? You can do dot diagrams for some covalent compounds, but it doesn't work for all of them. So I say no, okay? Let's not do it. So the first thing you want to do is add up your electrons, your valence electrons. So if you find fluorine on the periodic table, fluorine, halogen, it's got 7 valence electrons. So that's going to be 7, but you got 2 of them times 2. We got 14 electrons to build our molecule with. 14 electrons to build our molecule with. Okay? Next step, that's step 1. Add up your valence electrons. Don't skip that step. Don't do it. Everybody else skips that step. Don't do it. Okay? That's like how much money you got. We got 14 electrons to spend. The next step is to connect all the atoms with a single bond. Now, this is easy. There's 2 fluorines, so we're just going to connect them with a bond. Now, a bond is equal to 2 electrons. A bond is 2 electrons. A double bond would be 4 electrons. A triple bond would be 6 electrons, okay? So when I do a bond, if I put a bond, I just used up 2 of my 14 electrons. I got 12 electrons left. Okay? Okay. Next. Okay. I used up 2. I got 12 left. What do I do? Now I'm going to add pairs of electrons around the atoms. These are called lone pairs. I'm going to add pairs of electrons around the atoms to satisfy the octet rule for everybody. So I got 12 total electrons here to work with. So this fluorine on the left is sharing 2 electrons. So I'm going to add 6 more, 2, 4, 6. Now it's up to 8. See how it's up to 8? It's sharing 2 with the bond. So that's going to count as 2 electrons for this fluorine and 2 electrons for this fluorine. But right now we're just looking at the fluorine on the left. It's sharing 2 electrons here, and it's got 2, 4. I added 3 lone pairs, 6. So now that's got 8 electrons around it. Now we're going to do the same thing for this fluorine. It's sharing 2. I'm going to add 6 more. And I had exactly the right number of electrons. I had 12 electrons left. I spent 2, 4, 6, 8, 10, 12. I've got none left. This is my Lewis structure for molecular fluorine. I love this unit because this is for the first time when you can start to talk intelligently about molecules. So a molecule of fluorine contains a single bond between the 2 fluorine atoms, and each fluorine has 3 lone pairs of electrons. Okay, so again, you can start to talk about the structures. You can start to have an intelligent conversation. A molecule of F2 has a single bond between 2 fluorines, and each fluorine has 3 lone pairs of electrons. Let's try another one. Let's do CH4. That's methane. And the first thing we want to do is we want to add up the valence electrons. Okay, so we got 4 from the carbon, and we've got 1 from each hydrogen, but there's 4 hydrogens. That's 8 total electrons to build our molecule with. 8 total electrons. That's step 1, add up your valence electrons. Step 2, connect everything with a bond to the central atom. How do you know what the central atom is? Well, the atom that's written first, unless it's hydrogen, is going to be your central atom. That's the atom that goes in the middle of your structure. So put a carbon in the middle, and we're going to have 4 hydrogens coming off of it. 1, 2, 3, and 4. Okay, so if we look, I have spent 2, 4, 6, 8 electrons doing that. I am out of electrons. So man, do I hope everybody is happy. Let's check it. Let's look at the hydrogens first. Remember, hydrogen follows the duet rule. So as soon as hydrogen makes a bond, it's done. Hydrogen has got its 2 electrons. It's sharing 2. This guy's sharing 2. This guy's sharing 2. And this guy's sharing 2. Each of those hydrogens is sharing 2 electrons. Now let's check carbon. Does carbon have 8 electrons? The answer is yes. It's sharing 2, 4, 6, 8. It's sharing its 8 electrons. That's a happy molecule. Okay, that's a happy, happy, happy molecule right there. All right, let's do some more. Here's a very important molecule. How about water? So the first thing we want to do, we want to add up our electrons. Each hydrogen brings an electron to the party, so that's 2, right? Oxygen brings 6 to the party. Find oxygen on the periodic table. That's a total of 8 electrons. Now, the atom that comes first in a formula is the central atom, unless it's hydrogen. Hydrogen cannot be a central atom. Stop and think about it. If hydrogen's in the middle making more than 1 bond, it's going to have more than 2 electrons, and it can't do that. Hydrogen follows the duet rule. So hydrogen does not go in the middle, but oxygen will. So if hydrogen is written first, skip it. The next element will probably be the central atom. So we're going to put oxygen in the middle. We're going to have 2 hydrogens coming off of it. 1, 2. That's going to use up 4 electrons, leaves me with 4. So now the hydrogens are happy, but oxygen needs 4 more. It's got 2, 4, right? It needs 4, so 2 lone pairs, and there's my structure for water. Hydrogen is following the duet rule. Oxygen is following the octet rule. It's happy. Now, if y'all took high school chem, hopefully you know water doesn't actually look like that. Water is bent. It's got a bent molecular geometry. It's polar. Drawing the structures the correct way, that's called their molecular geometry. And that requires something called VSEPR theory. In lab on Thursday, I need to try to remember to give you a chart of VSEPR geometries for Monday, so that you have it with you for Monday. So somebody, please remind me tomorrow night to give you that VSEPR chart, okay? Because I'll have it, but if I don't remember to give it to you, that's not going to be good. So If somebody could remind me to do that, that would just be so awesome. Anyway, right now we are focusing on just trying to draw the Lewis structure with the correct connectivity. Okay, it actually looks like this, but we're drawing it. You can see, both of these structures have an oxygen bound to two different hydrogens, and it's got two lone pairs. Oxygen bound to two different hydrogens, and it's got two lone pairs. So like that's how we, right now we're not worrying about the shape. That's coming. That's coming. Okay. How about this guy? How about OF2? Try and draw the right Lewis structure for that one. Take a minute. You got this. Worst thing you can do is get it wrong. Here we go. Oxygen, 6 valence electrons. Fluorine, 7 valence electrons, but you got 2 of them. So that's 14. You got 20 electrons. So the first thing, did you add that up? Did you get 20? If you got 20, I'll give you a point. All right, you could have the ugliest Lewis structure I've ever seen, but if you got 20 electrons, I will give you a point for that. Right? I'll just, it's the little things. Next up, oxygen comes first, so we're going to put an oxygen in the middle. And connecting the 2 fluorines to it uses up 4 electrons. We got 16 left. So now that's 2. Oh, so now we want to make everybody happy. Okay. This fluorine is sharing 2, needs 6 more. So that's 2, 4, 6. Now that's happy. This oxygen sharing 4 needs 4 more. So it's 2, 4, 6, 8, 10. Now that's happy. This fluorine sharing 2 needs 6 more. 12, 14, 16. I used all my electrons. There's my Lewis structure for OF2. Now it is actually bent. So its actual shape is it looks like water. Okay, but for right now, I'm just worried about having the right connectivity. Again, really love this unit. You can talk intelligently about OF2 now. A molecule of OF2 has a central oxygen atom that is singly bound to 2 different fluorines. That central oxygen atom has 2 lone pairs of electrons, and each of the fluorines has 3 lone pairs of electrons. You could talk intelligently about molecules. You draw them, you can picture them, you can talk about them. It's a big chapter. Big, 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 big chapter. Okay. Let's have you try another one. I'd like you to try carbon tetrabromide. Give it a shot. Lots of electrons here, folks. All right. Here we go. Carbon bringing 4 to the party. Each bromine bringing 7. That's 28. We got 32 electrons to work with. Carbon going in the middle because it came first. 4 bromines coming off of it. 1, 2, 3, 4. Used up 8 electrons. 32 minus 8 is 24. Now, before you start going dot crazy, I like to ask myself, is anybody happy? The answer is yeah, carbon is. Carbon's got its 2, 4, 6, 8. Don't put any dots on carbon. Don't go put any dots on carbon. Carbon has got its full octet. Bromine does not. Now, I like to say there's 2 types of people, thinkers and doers. A thinker looks at this and says each bromine needs 6 more dots, and you got 4 bromines. Well, 6 times 4 is 24. So, you're going to be good. A doer just starts spending, right? 2, 4, 6, that's happy. 8, 10, 12, that's happy. 14, 16, 18, that's happy. 20, 22, 24, that's happy. There's your structure for carbon tetrabromide. Carbon tetrabromide's got a central carbon atom, singly bound to 4 bromines. Each bromine has got 3 lone pairs coming off of it. Carbon tetrabromide. How we feeling? All right, it's 8:21. Let's do double, triple bonds. We're not going to do resonance. We'll do resonance on Monday. Let's do double, triple bonds. We'll call it a night. Okay, so what do you do when you don't have enough electrons? Here we go. Please don't work ahead. Let's do this one together. So O2, we got to add up our electrons. 6 times 2 is 12. We got 12 electrons to work with. We're going to connect the two oxygens together. Used up 2, got 10 left. Take a second, catch up. Okay, now you got to think, you got to figure out if you're a thinker or a doer. Okay, here's what a thinker would say. A thinker would say this oxygen needs 6 more. This oxygen needs 6 more. That's 12. 12 minus 10 is 2. I'm short 2 electrons. Okay, you see how I'm short? I don't have enough. That's what a thinker does. A doer just starts spending, makes everybody happy till they run out. I got 10 electrons to spend. 2, 4, 6. That's happy. 8, 10. Uh-oh. Not happy. See how I'm short 2 electrons? Okay, so what do? Well, for every 2 electrons you're short, add another bond. So what do? If you're a doer and you put dots on here, this structure is now dead. Don't try to save it. Move on. You got to redraw it, so we're going to redraw it. But we determined we were short 2 electrons, so we need to add a bond. We're going to add a bond in the middle right there. So now I had 12 electrons to spend, but now this is a double bond. So I've spent 4 electrons, I got 8 left. So now if we look at this, this oxygen needs 4 more because it's sharing 4. This oxygen needs 4 more because it's sharing 4. We're going to have enough. Or you could say 2, 4, 6, 8. That structure is now happy. Oxygen has got a double bond between the 2 molecules, or between the 2 oxygen atoms in that molecule. Let's try another one. Okay. We're going to add up our electrons. Nitrogen's got 5, but I got 2 of them. That's 10 electrons. We're going to connect the 2 nitrogens together. Leaves us with 8. 2 types of people. This nitrogen needs 6. This nitrogen needs 6. That's 12, but I only got 8. I'm short 4. Or you could be a doer. I got 8 to spend. 2, 4, 6. That's happy. 8. This one is a double uh-oh. The double uh-oh. I'm short 4 electrons. Every 2 electrons you're short, you got to add a bond. We're going to add 2 more bonds to this. If you're a doer, you ruined this structure. Don't try to save it. Start over. So we're going to connect them together, but now we need to add 2 more bonds. It goes from a single bond to a triple bond. I had 10 electrons to spend. With a triple bond, I've spent 6. I got 4 left. So what do? That nitrogen needs a lone pair. Now it's got 8 because it's sharing 6. And this nitrogen needs a lone pair. Now it's got 8 because it's sharing 6. There's your structure of N2. Nitrogen, triple bond in there. Super strong, super inert molecule. 70% of the air you're breathing is that molecule right there. It's hard to do anything with it because to do anything with it, you got to break a triple bond. It's very hard. Lots of energy. One of the strongest covalent bonds found in nature right there. Okay. All right. All right. Let's do 2 more. 2 more molecules. All right. Let's do HCN. First thing, add up the electrons. Go ahead. And then we'll talk about connectivity. All right. So we got 1 plus 4 plus 5. You should have 10 electrons. Now, how do you put this together? Hydrogen cannot be a central atom. So we skip it. Carbon's going to be in the middle. With that, I want you to try. Can you put it together right? Give it a shot. That's the connectivity. Subtract 4. Think your way through it. You got this. All right. Used up 4 electrons, leaves us with 6. 2 kinds of people. Hydrogen's happy. That carbon needs 4 more. That nitrogen needs 6 more. I need 10 more electrons, but I've only got 6. I'm short 4. I'm going to need to add 2 bonds. Or You're a doer, and you say, okay, man, I got 6, 2, 4. That's happy. 6. It's a double. Uh-oh. Where's the only place you can add 2 bonds between carbon and nitrogen? Hydrogen cannot double or triple bond. So we're going to redraw this, and we're going to add 2 more bonds there. And now I had 10 electrons to spend. I spent 8. I've got 2 left, double or a lone pair on the nitrogen. There's your molecule of HCN. Cool. How we feeling? Hopefully okay. I want to do one more. I want to talk about how nature loves symmetry. Here we go. We'll do this guy together. COCl2. Let's add up the electrons. 4 for carbon, 6 for oxygen, 14 for the chlorine. That's 24 total electrons. Carbon in the middle. We're going to put an oxygen off of it and 2 chlorines. How did I know that? Carbon came first, central atom. It's got an oxygen and then 2 chlorines coming off of it, just like that. Okay? I've used up 6 electrons. I got 18 electrons left. Now, there's 2 kinds of people. A thinker says, all right, this guy needs 6 more. That guy needs 6 more. That guy needs 6 more. That guy needs 2 more. Right? So that's 20. I've only got 18. I'm short 2. Right? Or if you're a doer, you just start spending those 18. 2, 4, 6, that's happy. 8, 10, 12, that's happy. 14, 16, 18, I'm out, but it's an uh-oh. I am short 2 electrons. What does that mean? It means I need to add another bond. Where do I add that bond? You got 3 options. You can put it here, you can put it here, or you can put it here. The answer is, for now, until we learn formal charge on Monday, nature loves symmetry. The correct place to put it is going to be between the carbon and the oxygen. Like that. Why? Well, if you think about it, this molecule is going to have an internal mirror plane. If I would double bond one of the chlorines, that molecule does not have an internal mirror plane. So we want to double bond the oxygen because that is the most symmetrical molecule. So we're going to do the double bond between the carbon and the oxygen. Okay, and now we're going to start all over. We got 24 electrons. We spent 2, 4, 6, 8. That's 16 left. Carbon's happy. Carbon's got its full octet, 2, 4, 6, 8. The chlorines are not, though. They need 6 more, 2, 4, 6, 8, 10, 12. Oxygen's sharing 4, it needs 4 more, 14, 16. There's my COCl2. This is phosgene, nasty molecule, chemical warfare agent. Okay, but beautiful Lewis structure. Okay, it's got a double bond, excuse me, between the carbon and oxygens. It's got a single bond between carbon and 2 chlorines. The carbon has no lone pairs. Each chlorine has 3 lone pairs, and the oxygen has 2 lone pairs. So you can now start to talk super smart, right? Impress all your friends about these beautiful Lewis structures.